Hello there. In this lesson, we're going to learn about entropy. Entropy is a term that's used for a bunch of things, but usually in reference to the level of disorder or chaos that a system is in. So if we have a nice orderly pack of cards, that is a low amount of entropy. And if we have one that's spread all over the place, that is a high amount of entropy. And so chemical reactions can also have this property, of course, because some states of matter are more orderly than others. Entropy is also related to like the odds of something happening. A more disorderly arrangement of particles is a lot more likely than an orderly one. And so entropy increases when there is more disorder in the particles that you end up with. The symbol is given an S, and then of course the change would be delta S. So this would be positive delta S when you make your nice crystal into, say, a gas or a liquid, right? And then of course if you went this way, if you cooled something down or reacted something to make it more orderly, then that would be a negative change in entropy. So there's a bunch of different factors that affect the amount of entropy that a system might have. Temperature is one of them. We kind of alluded to that previously. The greater the temperature, the more the particles will move, the more they spread out, and that is a more random arrangement than if it's nice and cool and frozen and orderly. So if you are going from, say, a solid to a liquid, that's going to be an increase in entropy. If you're going to go from a liquid to a gas, that's an increase in entropy. And vice versa if you're going the other way. If you are removing energy and the particles are coming more closely together, then there's fewer options for how those arrangements can be, and therefore less entropy. State, of course, related to temperature. Solids are going to be lower entropy than gases. Liquids are in between. Volume. So if you let your gas expand into a larger space, well, that's going to be greater entropy than if it's compressed into a smaller space. In chemical reactions, if you have, say, some products that have atoms spread out into more particles, then that will be of greater entropy than if the particles were fewer and had more atoms as part of their structure. And then similar to volume of a gas, if you have a solution that is more concentrated, it's going to be of lower entropy than if it was less concentrated. Dissolving things is also related to entropy. When you have a nice orderly crystal, like in this example, some table salt. I'm not sure if this green is really working. Go back to red. Yeah, stands out a little better. Yeah, so if you get this nice orderly crystal here, then that is going to be of lower entropy than if you take all of those ions, spread them out throughout a solution, and surround them with water molecules. So in general, that's going to be an increase in entropy when you dissolve something, and then if you recrystallize it, that's going to be a decrease in entropy. Alluded to earlier, if your chemical reaction produces more particles, this tends to increase the entropy. So in this case, we have N2O4, and it breaks down and gives you 2 NO2s for each one of them, right? And so since there's more particles here and more random distribution of these atoms, then this is going to be an increase in entropy going in the direction of the products. If you can make those products go in the reverse direction, then of course that would be a decrease in entropy, and you would end up with a more orderly, larger molecule. Here's a little situation where we can make some predictions. Says first off, write a balanced equation for this reaction. So we've got these A2 molecules, and we've got these single B atoms, and they react to give you this AB compound, and we are going to need 2's here in order to balance. Then it says predict the sign, delta S, for the reaction. So how many particles we have here? It is 3. We get 2 B's and 1 A. Over here we end up with just 2. So particle-wise, since we're decreasing in particles, this is likely a decrease in entropy. So for a pure substance, you can think of the entropy as being related to how the particles are oriented with each other. And so because temperature is related to the motion of the particles, At a higher temperature, obviously the particles are going to be moving more and bouncing off each other more randomly, and that means greater entropy. And then at the other end, you have this third law of thermodynamics, where it can't get any more ordered. So if you're at absolute zero temperature, that means that if you have a crystalline solid at that point, that you can't make it any more ordered. The particles have ceased to move. They're as tightly bound as they can possibly be, and that's the 0 point. And so you can measure entropies based on the theoretical 0 point being at absolute zero and the amount of energy that you would need to add to get it to any other point along that sort of heating curve. You can see these sort of discontinuous jumps here at the state changes, where there is a big increase in entropy without the change in temperature. So you can see these tables include entropy values. See, the units of the entropy value are in joules per mole Kelvin. And so what that would be is using that zero entropy starting point, you just need to measure how much energy has been inputted to get that pure substance up to whatever temperature at. So the standardized one would be something like STP, and you see the little degree sign there for a standard measurement. And then you can make standardized temperature values, entropy values, by dividing the energy needed per mole by the temperature at that standard point. So using an entropy table, you can now work out an entropy change from reactants to products for any change that you might have, any chemical change there might be. The same thing we did with like enthalpy of formation. You just multiply the moles by the entropy value of your product, and the same thing for your reactants, and then you subtract them, and the difference would be the entropy change. So for doing this example here, we have 2 moles of NO2. So 2 moles times, and we'll look up NO2 on here somewhere. Yeah, there it is. 240 joules per Kelvin mole. So 240 joules per Kelvin mole. And we will subtract. We got 1 mole here, 1 mole, and the N2O4 is here, 304, 304. And so delta S for this under standard conditions would be, let's see here, 2 times 240 is 480, minus the 304, just finish filling this in, joules per Kelvin mole. I see the moles cancel out, no moles in the answer here, and we'll end up with 480 minus 304 equals, there it is, 176, and that would just be joules per Kelvin. So there you go, entropy change in a nutshell. Try some practice. We'll see you soon.